I am going to begin by talking about the relationship between hemodynamics and vessel depictability using optical coherence tomography and angiography. These are my relevant disclosures. 6 years after being introduced, the importance of OCTA is increasing in both clinical research and clinical practice as it evolves to include wider angles and higher image quality. However, the relationship between hemodynamics and vessel depictability using OCTA has not been clarified. An adaptive optic scanning light ophthalmoscope (AOSLO) enables observation of the fundus at the cellular level. It is possible to visualize and analyze the movement of blood cells in capillaries. In this study, we investigated the relationship between the hemodynamics observed using an AOSLO and vessel depictability in OCTA. We included 4 healthy young subjects with normal eyes in this study. The moving blood cells in the capillaries were visualized for the purpose of counting, and the blood cell density was calculated for each capillary. For OCTA depictability, OCT-A1 was employed. Capillaries in OCTA were analyzed and the detection rate was calculated as the rate of the number of OCTA scans depicting the target capillaries among the total scan number. We successfully recorded videos of all capillary networks. The video of the blood flow is shown in the upper left corner. The lower left image shows the blood flow visualized using a motion contrast technique. The perfusion map on the right was created by placing multiple images of blood vessels that were taken repeatedly. Blood vessels are depicted more finely here because the resolution is higher than that of OCTA. The blood cell enhancement process was performed using the video of blood flow obtained with an AOSLO, which ensured that the blood cells were observed with enough contrast to be clearly counted. We counted the number of blood cells per unit time and distance and derived the blood cell density for each vessel. Next, for each capillary, OCTA scans were analyzed to grade vessel depictability, and the detection rate was calculated as the ratio of the number of OCTA scans depicting the target capillary to the total scan number. As shown above, the number of blood vessel delineations vary across images. To summarize our results, 227 capillaries were identified using an AOSLO in the parafoveal capillary network. The mean blood cell density for all capillaries was 58.4 to 15.1 cells per millimeter. The mean OCTA detection rate of capillaries was 78.4 to 18.9%. This plot shows the relationship between blood cell density and OCTA detection rate. The vertical axis indicates the blood cell density, and the horizontal axis indicates the detection rate. A significant positive correlation was found between blood cell density and the OCTA detection rate. The higher the blood cell density, the higher the depictability of OCTA. Next, we created an additive averaged OCTA image using 10 OCTA images. The contrast of the blood vessels was improved, and each vessel was more easily recognized. Even after the averaging process, capillaries in the averaged OCTA were not identifiable. There were on average 3 vessels that were undepicted on averaged OCTA, among a total of 12 vessels. Approximately 5.3% of the vessels on averaged OCTA were not identifiable. This graph shows the relationship between the blood cell density and vessel depictability on averaged OCTA. Depicted capillaries in averaged OCTA had significantly lower blood cell density than other depicted capillaries. The mean OCTA detection rate of capillaries was approximately 80%. The type and speed of flowing blood cell vary in each vessel and change over time. In OCTA, images are created through live capture, and vessel depictability depends on hemodynamics. A significant positive correlation was found between blood cell density and the OCTA detection rate. The higher the blood cell density, the higher the probability of getting a decorrelation signal. It is thought that there is a depiction threshold. In the future, it will be necessary to estimate the blood cell density in diseased eye. Approximately 5% of vessels in averaged OCTA were not identifiable. It is necessary to improve the scanning method, such as by using VISTA, to enhance the depiction ability of single shots. Prolonging the interscan time is expected to improve visualization even of vessels with low blood cell density. In conclusion, vessel depictability in OCTA depends on blood cell density. Even in healthy subjects, vessels with extremely low blood cell density exist, and vessels in averaged OCTA are identifiable. Thank you for your attention.